To help us understand L'Hopital's rule, we need to go back and review limits. So find each limit. First thing you want to do is evaluate the function at the x value -1. So if I plug in -1 everywhere I see x, okay, this works out nicely. I get the number 4. All right, let's look at number 2. If I evaluate this function at -1, first of all, look at the denominator. Replacing x with -1, I'm going to end up dividing by 0. Okay, well, what happens when I replace the numerator with -1? Well, if you do the calculations, okay, you're going to end up with 4 over 0. And to remind you, we said that that limit does not exist. It's undefined. We're done, we move on. Look at number 3. All right, when you look at number 3 and you evaluate the denominator, you get 0. When you evaluate the numerator at -1, you also get 0. Okay, we call that indeterminate. There's further work that needs to be done with it. And what we did was we factored, and we looked to see if we could cancel a common factor. Well, it'd be convenient to cancel the denominator, x plus 1, because we don't ever want to divide by 0. So that kind of helps decide how you're going to factor the numerator. Okay, just trying to save some space here. If I were to factor out a 2, I'm going to get quantity x squared minus 1. Okay, and so continuing to factor, I then see that I can cancel these common factors of x plus 1 and x plus 1. Okay, so now it's a new limit problem. So evaluate at -1. So here, the limit answer then when you plug -1 in is going to be -4. Okay, so it started out to be indeterminate, but when we did a little more work, okay, we saw that we're going to have a limit answer of -4. So likely there's a point of discontinuity on this graph at x equals -1, but yet the graph is still going in from both left and right. The graph is still going into the y values of -4. Okay, L'Hopital's rule is going to give us an alternative to factoring. It involves finding derivatives. We're going to get the same answer of -4, but just using a different technique. Okay, so just kind of let you know here, we got indeterminate, and if we do get an indeterminate situation with a limit question, okay, we do have the option of not doing this algebra, but using what we call L'Hopital's rule, which we'll see in just a second. So let's continue finding some more limits. In this next group of problems, 4, 5, and 6, as you study what x is approaching a positive or a negative infinity. So in this case, we kind of switch gears and we think, okay, well, we're talking about end behavior of a graph. So if you were just to plug in infinity everywhere you see x, you're going to get infinity over infinity. Well, we call that also an indeterminate form. We can't determine anything from infinity over infinity. But you might remember that once we've identified this limit as a end behavior kind of question, what we did was, and we were dealing with a rational function. This is just a fraction of polynomials, top and bottom polynomials. Okay, what we did is we compared exponents in the numerator and denominator. So we see that the leading term has an exponent of 1 in the numerator. There's a 2 here. Because 1 is smaller than 2, we said that the answer was going to be 0. So we have a horizontal asymptote. As the graph comes on and leaves the screen, whatever this is doing, the y values are getting closer to 0. So that's kind of how we handled it. Well, after L'Hopital's rule, we're going to have another way that we can find this, this 0 without having to compare the degrees of both the numerator and denominator. Okay, so over here, same thing. We're dealing with end behavior. We identify the greatest exponent, numerator, denominator, because these are equal. Okay, we took a ratio of coefficients, and we said we had a horizontal asymptote at 3/2. All right, number 6, same thing, end behavior, compare the degrees. Okay, now how we handled this situation where 3 was larger than 2, the numerator degree was greater than the denominator's degree, how we handled that was we said, you know what? Okay, let's kind of simplify this problem. This rational function, okay, is behaving like just 3x cubed over x squared behaves at its ends. So whatever this graph is doing as it comes on and leaves the screen, so is this more complicated rational function. So what we did is we captured the model, we simplified, and then we plugged in negative infinity. Okay, so maybe here I should say this is approximated by. Okay, so let me simplify the model. Okay, so x squared cancels with that, so I'm left with 3x. That's a 3x. Okay, so whatever this function is doing at its ends is modeled by what this linear function is doing at its ends. So, I mean, you can either think graphically, this is a linear function that rises, so as I'm approaching negative infinity, the y values are getting smaller. Or simply plug in negative infinity for x now, and you're going to end up with negative infinity as the answer. So this is not a horizontal asymptote, it's what we called a slant asymptote. As you can see, the next three problems are the same problems in 4, 5, and 6. I just wanted to give you a preview of Hopitals' rule for these problems right here. We'll just use the rule and then we'll go to the more formal notes that we have on the other worksheet. Okay, Hopitals' rule says this: if you have an indeterminate limit, that could be 0 over 0, it could be positive infinity over positive infinity, or even negative infinity over positive infinity, or any combination of an infinity over an infinity, whether those be positive or negative. Okay, that's indeterminate. More work has to be done. Up here we knew we had to do some algebra. Here we knew we had to consider end behavior. Okay, well, Hopitals' rule says you can avoid all those, strategies and find derivatives. Okay, so here's what it looks like. Okay, when you plug in infinity, you notice that you're going to have infinity over infinity. Yes, it's indeterminate. This rule only works if you have an indeterminate limit. So if you discover that you do, then we say that this limit, I'm going to come down here, is equal to, it would have the same answer as the limit we would find if we were to find the derivative of the numerator, which is 3, and the derivative of the denominator, which is 4x. Retry plugging infinity in, you're going to get 3 over infinity, and we know if this is a super large number down here, that the answer, the quotient, is going to be 0. We get the same answer we got up here if we consider the topic of end behavior, comparing the degrees of the leading terms on top and bottom. So it's an alternate way. Okay, I'm just a little concerned about this technique just because, if you're trying to find this derivative right here without a limit problem, we would have to use quotient rule. So it's kind of easy to kind of confuse the two techniques. Quotient rule, but remember you're not dealing with a limit, okay, or Hopitals' rule where we actually just find the derivative of top and bottom, which we've never done before. If we were finding the derivative of a quotient, we always had to use the quotient rule. Or bring the denominator to the top and use product rule. So just kind of be, cautious about that. Okay, so let's look at 5a. Okay, again, plugging in infinity initially gives us the indeterminate form. Hey, yeah, I can use Hopitals' rule. Okay, so this limit is also equal to the limit of the derivatives of numerator and denominator. So we get 6x on top and 4x plus 5 in the denominator. If you tried to plug in infinity, again, we're going to have another indeterminate form, infinity over infinity. Well, the wonderful thing about Hopitals' rule is you can continue to find derivatives until you get to a point where you can evaluate the limit. So working down, find the derivative again. Okay, and make sure and bring the limit statement down. I mean, this fraction by itself means nothing. We can't apply Hopitals' rule if we don't have a limit situation. So down here, the derivative is 4. We just simply simplify that and we get 3/2, which is what we found using the end behavior idea previous. Okay, so in this problem we should end up with a negative infinity like we did previously here. Okay, if you were to plug in negative infinity, you're going to get negative infinity in the numerator. Because the most impact on the numerator's value is going to be, from the leading term here. So negative infinity cubed is negative infinity times 3, which is still negative infinity. In the denominator, I'm going to square a negative infinity, so I guess that gives me positive infinity. But as mentioned previously, this is still an indeterminate form, even though you have a combination of a positive and a negative infinity. So we can use Hopitals' rule. So this limit is equal to the limit of the derivatives of numerator and denominator. So what, 9x squared minus 5 and 2x here. Again, we're going to get an indeterminate form, so continue finding derivatives, okay, until you're able to evaluate the limit. So what, 18x over 2? I could simplify that and get 9x. And then I can plug in infinity. And what happens is 9 times negative infinity is still going to be negative infinity. Same answer we found in the first 6 that we did up here. All right, let's take a look back at 3 and applying L'Hopital's rule to the indeterminate rational function here. Okay, so instead of factoring, you determined that you have indeterminate. Okay, find derivative of numerator and denominator. So numerator is 4x, denominator is 1. Okay, I can't simplify it any further. Each step of the way, when you find derivatives, try and evaluate the limit. Plug in -1 times 4 gives -4. So L'Hopital's rule just provides an alternate way to evaluate a limit if we have an indeterminate form. So in the next video, we'll look at some more formal notes of this technique.